We begin with the conditional mean and the simplest local average, then move through kernels, local polynomials, bandwidth choice, multiple covariates, inference, code, and the connection to regression discontinuity. The chapter closes with a practical checklist and summary. Our goals are to define the conditional mean target, compute local average and kernel estimators, understand why local linear regression helps at boundaries, explain bandwidth and dimensionality, implement the methods in both languages, and connect them to regression discontinuity. A parametric regression commits to one global functional form, such as a line or quadratic. If that form is wrong, the resulting bias can remain even in a very large sample. Nonparametric regression keeps the target, the conditional mean, but learns its shape locally from nearby observations. It is not assumption-free. We replace a global polynomial assumption with smoothness in small neighborhoods, and the bandwidth becomes the main complexity choice. The comparison clarifies what changes and what does not. Parametric regression specifies one equation across the support and risks misspecification. Nonparametric regression builds many local approximations and risks high variance, where data are sparse. In both cases, the target remains the conditional mean. The key tuning decision shifts from choosing polynomial terms to choosing a window or bandwidth. Flexibility is purchased with local information, so the density of observations becomes central. The air pollution figure motivates that local perspective. The curves relate healthcare use and particulate pollution to inversion strength. Negative values indicate ordinary days. Positive values indicate warm layers trapping pollutants. A global polynomial would struggle with the change in shape near the threshold and in the right tail. The dashed density curve adds an essential warning. Estimates are most stable near zero, where observations concentrate, and less stable in sparse regions. Two ideas run through the chapter. First, nonparametric estimates are most informative where observations are dense. Pursuing low bias in a thin part of the support can create severe variance. Second, regression discontinuity needs the conditional mean immediately to the left and right of a known cutoff. That is a local estimation problem, so the same bandwidth and boundary issues appear. We develop the statistical tools first and return to their causal use near the end. At a target value, an estimate is only as informative as the observations nearby. In a dense region, many points receive weight, variance is lower, and local shape can be estimated stably. In a sparse region, few observations are close. The estimate becomes sensitive to bandwidth, and extrapolation-like behavior can reappear. Whenever you read a smoothed curve, look not only at its path but also at where the data lie along the horizontal axis. Suppose we want the expected price of a 50 square meter apartment. The most literal estimator averages only apartments of exactly that size. It is unbiased for the target under random sampling, but the number of exact matches is tiny, so the estimate is noisy. The central idea is to borrow information from nearby sizes. We accept a small amount of smoothing bias in exchange for a potentially large reduction in variance. For a continuous covariate, exact matching is too demanding. Replace it with a local window. Include every observation whose covariate lies within a chosen distance of the target. The bandwidth is the half-width of that neighborhood. A wider window raises the effective local sample size and lowers variance, but it also admits observations farther from the target and can increase bias. That single choice already contains the chapter's bias-variance trade-off.